Okay, thank you very much for inviting me, for organizing this. I started my career as an unemployed physicist, like most people, many of my colleagues do. Let me start because I tend to lose track of time to the dismay of people, so I can be interrupted at any point. So this is the conclusion. So this is about, as I say, force fields, and force fields is a concept it's a relatively elementary concept that combines geometry and physics, and so they are essentially the property of being observable, and they somewhat turn out to be expressing very well the relationship between the activities in the brain and the resulting behavior through the interaction in the environment. And one thing that made them attractive to us is that they are inherently additive, and so they can be considered as motor primitives that can be combined to generate more complex pattern of control. And so what I hope I can also discuss is the possibility to use force fields as mechanisms to somewhat represent learning, that is the ability to build operational knowledge based on sensory motor experiences. I don't know if I have time in this context. I possibly go to the very last part where I would describe how this concept may guide to different type of brain-machine interfaces, but I would start from the basis of it. So let me say here, this is a very old kind of, it doesn't matter that there is a movie or not, but is a relatively old-fashioned robot machine, right? And I started to work in motor control, or study hand and arm movements. At the time that was very interesting. It was essentially a time where there was somewhat of a paradigm shift from, say, linear one-dimensional control to nonlinear multidimensional control. And that paradigm shift was largely brought by parallel developments in robotics. That is, people in robotic engineering had to control these things. They call them arms, although they don't look really like human arms, of course. They're made with different things. And they had to solve problems such as doing an inverse kinematics, that is, given a desired path of the end effector, which is a six-dimensional object, you wanted to compute how the different degrees of freedom of the machine have to move. And so this is a problem of nonlinear geometry. And then once you have solved this path planning or path planning problem, then you have to think of how to generate the appropriate motor forces, right? So you have an inverse dynamics problem. These are the lingo that developed in the early 80s, and people turn out writing pages of equations because this is essentially Lagrangian mechanics is F equal ma, but if you have to write it for a multidimensional systems, they become very long and tedious. But so let's say, while on one hand, what I want to stress is that this robotics and conventional engineering has some very remarkable, important differences with respect to the way in which the brain controls natural movements. But on the other hand, one thing that came and was evident is that some of the problems that were not considered before this age were problems that our brain have to solve one way or the other. How does it solve is not is still largely unknown, but it puts the focus on that. So this is somewhat, you see here the way computer programs. This is a very simple MATLAB code, but there are obviously different way of doing it, and it would be very hard to think of this as something that is in our brain in this format, at least. So this leads to another point, that is the point of representations. And a good description of the concept of representation is from the book of David Marr's on its vision. And so this is a little statement about numbers. So, but this essentially is points out the importance of representations in the way you solve problems. It's interesting here, shows that how the Roman numerals was a particular representation that was very unfortunate, so that you couldn't do certain type of operation, whereas the Arab numerals is a representation that lends itself to certain type of operation. So the representations are actually, the issue of representation is very important. And so I would like to start a little bit from what kind of representation makes sense from a biological perspective. And the idea is that what is the ultimate symbolic elements, the ultimate elements that the control system has to refer to in biological control. And in a sense, this is the muscles, is the neuromuscular system that has certain properties. And I'm trying to suggest here, what I'm trying to convey in this talk is the concept that the mechanical properties, certain properties that appear to be non-ideal, okay, in our muscles, are actually extremely important in determining how the nervous system then can build computations on top of them. And I'd like to start from something which is the concept of what is an ideal force generator. So when you go back to these robotic systems like the Puma or like any robotic system, people use torque motors. They use motors. So motors, ideally, if you want to build a robot, you would go to something that is similar to an ideal voltage source. So you want something where the force produced is a function of a control variable, like the voltage applied to the motor, and does not depend on state variables, on position, on velocity. So you want to be sure that if I put 10 volt, I get that many Newton meter torques, regardless of the speed and the position at which I operate. And of course, real devices are approximation of that, but there is an effort to produce force generator in that fashion. Now, if you look at muscles, okay, this is just one of the many very old studies by Rack and Westbury of how muscle work in a cat soleus. What basically they did, they stimulated electrically in a relatively soft and natural-like way the nerve of a cat soleus muscles and measure the isometric force at different value of length. And so you see that those curves don't look like those curves. Okay, so in other words, muscles have what people call impedance. So they can say, well, they are not a very good force generator. Okay, they're not a good force generator, but you can turn things around, and the fact that they have this behavior carries some other advantages. Okay, in the way computation can be carried out by the neural controller, and in fact, not only the neural controller may take advantage that these are not flat lines like those, but also by the fact that those lines are nonlinear. That is, they're not. The fact that they're nonlinear can have a significant, important implications. So let me begin. So what is that one needs to represent? We were talking about representations, and if you look at in terms from the point of view of control, one thing that you may want to represent is what is called a control policy. Okay, control policy. If you look in certain text, reinforcement learning, or control policy essentially is a function that generates an action given a certain goal and certain state at the interface with the environment. So this is a sort of a general definition. Now, if you think of an action of a force as a force that you produce in a system, effectively a control policy is a field. That is a field where you have a force that depends upon a state, can be a generalized force, and also it has as a goal. Once you set a goal, you generate a force. So you can think of a control policy in a motor system as a generalized kind of field. And if I can go to the next. So the point here is that muscle and muscle synergies are somewhat can be seen as mechanical basis functions. And so the point is that can be seen as basis functions through which a system constructs control policies. When I say muscle synergies, is a sort of a loaded term. So it's the fact that our brain does not control one muscle at a time, but usually controls multiple muscles that act together. So if you try to strip some of this broad concept, you can think of a muscle essentially as an element that generates a force as a function of the state of length and time, right? So and you think of, in this case, it's a simplified version where you consider a scaling function, but it doesn't have to be in this form. But roughly, you say if you think of isometric force, if you activate a muscle with different level of input, of driving input, you can scale a function of length and lengthening velocity, right? So if you now consider an assembly of muscles that acts around the joint, basically what you can construct a slightly more complex function where you have a state in terms of a configuration space of the arm, and again, so you can think of it as a sum of these elements. So you can think of those phe's as building blocks for constructing policies. Now, one thing that is important is that the fact that those the phe's are not linear. It's an important factor because it's important if you think from the point of view of generating policies by superposition of basis functions, because linear functions are not a good basis function, of course, because they only generate other linear functions. Not even polynomials are good. So in a way, you want to have some serious non-linearity in order to produce a repertoire. Now, this is a somewhat abstract concept that you can see muscles in this way. Can they be seen in this way? So this concept were connected to some experiments that we did 20 years ago on spinal frogs, and that have been repeated on rats and on other preparation. And they somewhat support these simple concepts. And the idea is that if you stimulate, say, the spinal gray matter in a frog, and you measure the peak force while you place the leg at different location, you measure different forces. You apply the same stimulus, you see different forces. And if you just do a simple interpolation of this measurement, at the end you typically see something like that. Now, this field, this is a force field, and it has some relevant properties. One of them is that it's a field that tends to converge to a point where it's zero, so it's a stable equilibrium. But the other thing that one has to keep in mind, that this is nothing special, nothing strange. If you think of the muscles as a spring-like elements, this is pretty much what you have to expect to happen if you activate those spring-like elements. So this is somewhat you can think of it as a simple kind of a basis function or a basis field. And of course, if you stimulate, the field is not a static thing, but it moves. This is a sequence in time. So you can get something like a movie. So there is a whole way. There is a very large literature in the spinal motor control about pattern generators, central pattern generators, spinal pattern generators, and this is not anything substantially different from that. It's just saying that the output of a pattern generator is something of this kind. Conceptually, what a field means is that what the brain can do. The brain cannot tell exactly what will be the movement, what will happen, but essentially the brain can tell what kind of negotiation will take place with the environment. And so if nothing happens, if I'm moving in free space, probably the brain will tend to the activity of the muscle will tend to drive a limb along a trajectory, right? Which is specified as somewhat of a set of attractors. It doesn't have to be, a field doesn't have to have this shape. You can also think of circulating shape. You can generate cyclical motions and so on. So this is one particular case. But essentially, what an object without changing in time And the only way to do it is by applying the correct force profile against a rigid constraint. Strangely enough, it seems to be a difficult task, but subject learned to do it very well. And so what we did in these experiments is to compare the experimental results with the model. Actually, with two models. We use a model where you do cancel the force by force feedback, and the other where you cancel the force by learning the motion field in the environment. And so here is how a force controller would work, where you have in this case, you have to produce a force in this direction. So when you act against a rigid constraint, there is no motion, and you have a force that moves in this direction, and you have zero motion. And that's pretty much what the subject learned to do. Okay? And when you change the environment, the contact point, the contact becomes soft all of a sudden. So instead of being rigid, the environment becomes, it becomes a viscoelastic environment. As a result, initially you have a force that is different from the force that you want to produce. If you had a force controller, actually, the force controller would be able to catch up relatively rapidly, whereas subjects are not. And in fact, the subject behavior is similar to the one predicted. And most importantly, what you have at the end is that if you, this is at the end of learning, where subject recover the behavior, and at the end, if the environment is restored as a rigid constraint, you see this after effect, which is in the direction predicted by the model. So effectively, you see result in force control that mimics very closely the result of adaptation in motion control. So that is somewhat wrap up the story in the sense that you know, it seems that, again, that what subjects are capable to do in both type of tasks is to form a representation of how the environment responds to the actions, either those being movement or being contact forces that are applied. So these were the conclusions. And do I have any left, or we have 5 minutes? So I can just go rapidly in 5 minutes to this concept of the the brain-machine interface. And the brain-machine interface is a field that has been growing lately. But usually what happens in brain-machine interface, what is the dominant paradigm, is that of decoding activities to produce desired trajectories, right? So the concept is that you're reading from either different possible brain areas, and you try to find out what is the motor intention, and then you have some device and you control the device. Now, one thing that is attracting increasing interest is considering the interface in the other direction, that is not only decoding movement from intention from brain activity, but also possibly sending back sensory information. The form of, because the way in which the information is sent back is by electrical stimuli, which has a lot of problematic aspect to them. But so you can think of that. One of the way to think of this is that, well, you can convey to the brain information about the state of a control device, and then that would provide the brain with the possibility to react more rapidly. But another approach could be that, or it would be that of having two parallel interfaces. This is experiments with a group in Genoa in the IIT, which is carried out on rats, on anesthetized rats, where you have a sensory. You have two arrays. One is an array of stimulating arrays in a sensory area, and one is a recording array in a motor area. And basically, what you have two processes. One is encoding you have a workspace, and you have a dynamical system. In this case, the dynamical system is in the first implementation is a simulation, is a point mass that moves in a fluid, and the state of the dynamical system is a point, and on this plane. And so you want to find out how to stimulate or produce a stimulus that encodes the state and send the state information to the somatosensory cortex. And as you produce a stimulus, also you are going to have, because of some pattern of connectivity, which possibly evolve with practice, but what you have activities that you record on M1, and these activities are decoded into what? They're decoded not into a motion, but into a force. So effectively, you can use this framework to program an interface to produce something equivalent to a force field. Now, a force field in an approximation sense, in this case, and so in a very first implementation, the force field can be continuous, or it can be also in a very rudimentary way. You can divide the workspace into a set of regions, like in 4 regions, and have that in each region there is a corresponding force. And so this would be like a piecewise continuous approximation. And depending on the state, if the state is here, for instance, you will apply at this point the same force vector. You can look at it as a lookup table, so you would produce this force. So this would be a very coarse approximation of a convergent field, and then you apply the force vector. And when you generate a stimulus, when you produce the stimulus, you would actually see a variable response, because this is a real brain, and so you don't get always the same force, but on average you get a distribution of forces that on average goes in this direction. And so again, you have effectively in this framework you have a desired field, which is something like this with a very simple pattern. But again, in this case the field is convergent. It can be a circulating pattern, can have different shapes. The point is that if you approach it as a lookup table, you reduce this to a finite set of regions, and then with the noise you get something more confused than what you wanted to have. But nevertheless, the experimental result suggests that in a large majority of cases, despite this very rudimentary form, you have that the resulting trajectory controlled by this system tend to converge to the central equilibrium, tend to be a relatively regular trajectory. So this is it's just a framework to think of the interface not as a simple decoding mechanism, but as a model in which the sensory information and the motor output are simultaneously calibrated to produce a dynamical behavior. So what I think it will make sense, this is just at this point is just an idea, but is the idea that what you may want to do in a brain-machine interface is not so much to decode an intention into a movement, but you may want to decode an intention into a dynamical behavior. And the movement is a particular dynamical behavior that takes place if the environment is, is free space. But if the environment is not free space, you can think of a dynamical behavior as a prescription of forces given the state in which the system is moving. So this is I think that's it. And this is work that has, through the years, has been started with at MIT with Emilio Bizzi and Neville Hogan. Many of the concepts of this impedance control came largely from early seminal work of Hogan. The work on the frog also with Simon Gister, the learning with Reza Shadmer, and more recently the force control and the work on the interface has been with Maura Casadio, who is now at faculty in the University of Genoa, with Amir Karniel, that you know well, we still collaborate, and Asaf, and the group in Genoa, and other people listed here. Thank you.